Dames en heren, ladies and gentlemen, geachte collega's, dear colleagues, I hereby formally open this session and I welcome you all to the public defense of Mr. Joey Stephanus Gradus Mombarg. Mr. Joey Stephanus Gradus Mombarg has presented to the faculty his PhD thesis on the topic Asteroseismic Modeling of Intermediate Mass Stars in partial fulfillment of the requirements for the degree of PhD in Science, Astronomy and Astrophysics. He shall now publicly defend his PhD thesis. Maybe seated. Mr. Joey Stephanus Gradus Mombarg, you are invited to give a presentation of about 45 minutes about your work. Afterwards, the examination committee will ask questions and discuss your work with you. I now give the floor to Mr. Joey Stephanus Gradus Mombarg.
All right, imagine yourself looking up at the sky on a warm, clear summer night. If you were to look very carefully, or maybe if your eyes are a little bit better than they actually are, you would see that stars have different colors. If you then were to sort the stars based on their color, or equivalently their effective temperature, putting the bluer, hotter ones on the left and the cooler, redder ones on the right, and then in the other direction, sort them by their intrinsic brightness, or luminosity, you would arrive at what we call as astronomers the Hertzsprung-Russell diagram. And in this diagram, you see that there are certain regions that are more densely populated than others, because what you see here is stellar evolution and stellar structure in action. So stars, they drive the chemical evolution of our universe. They are the host of exoplanets. And so to understand how a universe works, it's important to understand how stars work. So let's first start with an intermediate mass star. So I studied intermediate mass stars during my PhD, which are stars that are slightly heavier than our own sun. So first, we're going to look at a star that's 1.5 times the mass of our own sun. Just like all stars, they form from a molecular cloud when it contracts under its own gravity. So it moves down in the Hertzsprung-Russell diagram. At some point, the material becomes opaque, and then it moves to larger temperatures. And when stars form, they are about 3/4 hydrogen, 1/4 helium, and a tiny fraction of what we call metals, so everything heavier than helium. After the main sequence, the temperature in the core is high enough to ignite hydrogen or start hydrogen burning. So it fuses hydrogen into helium in a convective core with an envelope where the energy transportation is done via radiation, so a radiative envelope, and maybe a very tiny convective outer layer on top of that. So this corresponds to this large band in the Hertzsprung-Russell diagram that I showed you before. Stars roughly spend 90% of their lifetimes on this main sequence, and this is the phase that I've studied during my PhD. After the main sequence, it will move up the red giant branch, where it fuses hydrogen in the shell around the core. It will then go on to be a red clump star, where it burns helium inside the core. It then moves upwards again to the asymptotic giant branch, where it fuses helium and hydrogen in shells around the core. And finally, it will shed its outer layers in the form of a planetary nebula, and what we end up with is a white dwarf. So while we know quite well how stars evolve, but there are still certain things that we do not understand fully. And so during my PhD, I tried to address these open questions in stellar evolution. So the first one concerns the transportation of what we call angular momentum. So if you're not familiar with angular momentum, so if you have an object, a solid object that is spinning, the angular momentum is then defined as the moment of inertia times the angular rotation frequency. And just like Earth, stars rotate. And so as the star evolves, the core starts to shrink, starts to spin up, the outer envelope expands and slows down, unless you also have some mechanism that transports angular momentum or rotation throughout the different layers of the star. And so our current models, they overestimate the core rotation rates that we measure in red giants by about 1 to 2 orders of magnitude. So if we look at the observational constraints, so what I'm showing you here is the measured rotation rate for, on the left, the core hydrogen burning stars, so the stars on the main sequence, and then on the right, the core helium burning stars, so the older ones. So what we here have is the surface gravity as a proxy for the age of the star. But so if you want to understand what already happens during the main sequence, so on the left side of the diagram, this surface gravity is not accurate enough to really see how this rotation evolves on the main sequence. So I'm showing you the typical error bar that we get on the top of the plot, and so this is quite large. So what we want to do is to do better and replace this surface gravity with an actual age of the star. And so secondly, concerns the uncertainties that we have in the mechanism and efficiencies that drive chemical or transport chemical elements in the star. So I'm showing you here is one of the fundamental equations of stellar evolution. Don't be scared. So all you need to know from this is that the change in the chemical composition over time for a specific element is due to nuclear reactions. So elements change due to nuclear reactions, and then we have a part attributed to the mixing, and these are characterized by these diffusion coefficients. And so we split this up in microscopic mixing, so you can think of this as stirring your pot of coffee, for example, with a spoon. And so these are large motions that mix all the material the same way. And then we have microscopic mixing, which is element specific. Now, for the microscopic diffusion coefficients, we don't really know what this value should be, what it should be as a function of time and as a function of radius. And for the microscopic mixing part, it's computationally very hard or more expensive to compute this. So let's start with the microscopic mixing part. So I'm showing you here is this microscopic diffusion coefficient as a function of where you are in the star. So in the convective core, everything is almost instantaneously mixed. So you have a very high value of this. And then just outside of the core, we don't really know what this mixing value should be. So this could be mixing induced by just an interplay of the convection between the core and the envelope, or due to some shear, due to rotation. So for this region, we don't know what the shape should be. So I'm showing you two commonly used functions for this. And we don't really know what the width of this region is, what we characterize with this FOV or alpha OV parameter. Okay, why is that important? So what I'm showing you here is the evolution tracks, again in the Hertzsprung-Russell diagram for stars where we vary this FOV parameter. And as you can see, if we have a higher value, you mix more material into your core, and as a result, your star will live longer. So to get accurate ages and to see how the stars precisely evolve, we do need to care about this parameter. So one of the classic ways of studying stars is via spectroscopy. So what you do there is you split the starlight into different wavelength bins and then compare the absorption lines of the different elements in the star with atmospheric models. And this way we can get properties such as the surface gravity I mentioned before. So this relates to the mass and the radius of the star, the effective temperature, and the surface metallicity, so the fraction of metals at the surface. But so in my thesis, I've also worked on astroseismology. So this is a study where we look at the interior of stars. But first, what I'm going to show you here is a water droplet that is suspended into an acoustic field and is then brought into resonance. And what you can see here is that there are certain motions that this water droplet likes to sort of oscillate or vibrate in what we call the eigenmodes, or modes of the water droplets. So similar, stars have these eigenmodes too, and they are characterized by three different numbers, so three different quantum numbers. So the first one is the spherical degree L, which gives you the number of surface nodal lines. So these are the white regions of the animation that don't change. So this is where the material doesn't move. Then we have the azimuthal order M, which gives you the surface nodal lines that cross the axis of symmetry. So in these animations, it's pointed upwards. And then lastly, we have the radial order n, which gives you the number of nodes in the radial direction. So we have different classes of stellar pulsations based on the restoring force. So the first one are pressure modes. They are acoustic modes, and they are restored by the pressure force. And these are mostly sensitive to the outer layers of the star. But the ones that I've studied during my PhD are the so-called gravity modes, or G modes, and these are restored by the buoyancy force, and they are most sensitive to the stellar interior, or the conditions in the stellar interior for stars that are on the main sequence. And these waves can only propagate into radiative regions. So if you have a star like our sun, I'm showing you here, where you have a thick convective outer envelope, they're trapped inside of the star, so we cannot observe them. But if you go to higher masses, you have a much thinner convective outer envelope, and then these waves reach the surface and we can observe them. Our water droplet was, these modes were brought into resonance with an external force, but stars can do this themselves. So there are different ways to do this. I'm only going to discuss the one that is relevant for these kind of modes that I've been studying, which is due to a heat mechanism. So imagine you have some photons coming from the core, and at some point they hit a layer where the flux is temporarily blocked. So this could be because if you have a partial ionization zone, for example, that contracts, then the opacity increases, while normally it would decrease. Or when you have a transition between a radiative and a convective zone. So this then blocks the flux temporarily. This causes the material to heat up, to expand, and so at some point the layer can no longer block the radiation, so the radiation can escape and everything is restored again, and this cycle then repeats. So this is a bit different from seismology on Earth. So these modes are constantly driven over, and they're like stable or coherent over the course of years. So the reason we can now do this kind of study is thanks to the NASA Kepler mission. So what Kepler did is stare at a patch of the sky for 4 years long. So it's just above the Cygnus constellation, just above the galactic plane. So here it has measured the brightness variation about 200,000 stars, taking a measurement every 29 minutes or so. So what we get from Kepler is the brightness variation of a star as a function of time. And when we do a Fourier transform to this, we get to a frequency amplitude spectrum. From this, we can extract the pulsation modes of the star. So the cool thing about these gravity modes is that they show regularities in their periods. So if we look at the difference in period, or the period spacing as it's called, between modes that have the same L and M value, but consecutive radial order, so a difference of 1 in M, for a star that is chemically homogeneous, not rotating, non-magnetic, this is a constant value. So I'm showing you here is, again, so the difference between two peaks of pulsations, and then this difference plotted as a function of the period itself. Yes, so as your star evolves, it starts to fuse hydrogen into helium into the core, and so what you get is a difference in the mean molecular weight when you go from the core to the surface, or a chemical gradient as we call it. As you can see in this animation, so this XC value is the hydrogen mass fraction in the core, so this decreases as the star evolves, and we use it as a indicator for the age. And so as the star evolves, you build up this chemical gradient, and this causes certain modes to be confined or trapped in a specific region of the star. So you can think of this as you have a rope with two different densities, and you have mode reflection at the interface point. And so as your star evolves, this chemical gradient becomes larger and larger, and so you'll see that more modes start to become trapped. And so the trap mode change their pulsation period, and this translates into these dips inside of your period spacing pattern. And so if your star evolves, you start to see more and more of these dips inside of your period spacing pattern. All right, so the other uncertainty on the mixing that I have not discussed yet is the envelope mixing. So we don't really also know what the mechanism or mechanisms is that drive this kind of mixing and what the efficiency should be. So right now we're just going to assume it's a constant value, this D0. So if you have a higher value for this D0, it means you mix your material more efficiently, so you are not able to build up this chemical gradient very well, and this translates in a reduction of your dips inside of the period spacing pattern. So the more mixing you have, the less pronounced these dips in the period spacing pattern are. So this is a nice way to probe the mixing efficiency inside of stars. And secondly, what we can do with these period spacing patterns is also measure the rotation rate of a star. So as a star rotates, these modes are Doppler shifted, and this induces a tilt inside of the period spacing pattern. And so the slope of this tilt is related to the rotation rate. So a higher rotation rate means you have a much steeper slope. So the type of stars that I've been studying during my PhD are the so-called Gamma Doradus variables. So they're named after the prototype Gamma Doradus in the Dorado constellation. And so they only officially defined as a class of pulsators not that long ago, so in 1999. These are intermediate mass stars, so 1.4 to 2 times the mass of our own sun. They are on the main sequence, so they are hydrogen burning in a convective core with a radiative envelope. And they show these large number of excited gravity modes, making them very nice candidates to study what is going on inside of stars. So yeah, they're situated right there in the Hertzsprung-Russell diagram, along with other types of pulsators. So during my PhD, I tried to answer 4 science questions. So the first one is which stellar parameters we can constrain combining astroseismology with spectroscopy. Secondly, if there are any correlations between the measured mass, the age, the rotation, and the core boundary efficiency of the star. Whether microscopic mixing is relevant in slowly rotating gravity mode pulsators. And lastly, if we can reproduce the measured chemical gradients using microscopic and rotational mixing. So I'm going to discuss all of them, of course. So we do this by way of forward modeling. So what that means is you start with a set of observations, so ideally a large sample of stars. You couple this to your first generation of models, and this allows you to infer different or fundamental parameters of the star, such as the mass, the age, the mixing efficiency, and whatnot. And so this then allows you to see what kind of physics is missing in your models, or give you a clue about what you can do to improve it. So this can sway to a new generation of models that you can couple back again to the observations, and in turn make more accurate or more precise measurements, or even measure things that you could not do before. So this PhD work has done the largest and most detailed astroseismic modeling effort for these kinds of Gamma Doradus pulsators. So let's start with the first question, what we can learn from astroseismology and spectroscopy combined. So where we couple the observations to the models. So we do this by using a seismic diagnostic called the buoyancy travel time. And this depends on what we call the Brunt-Weiser frequency. And so you can think of this as a sort of the frequency of a mass element that is displaced inside of a fluid. And this frequency tells you where in the star the modes are sort of situated. So in this green region in the plot that I'm showing you here. And so the dashed lines are the different radial orders of the gravity modes, and then the points are where the nodes are situated. So as your star evolves, the shape or the profile of your Brunt-Weiser frequency changes, and as a result, the buoyancy travel time changes as well. So this gives you a quite strong diagnostic on the age of a star. All right, so how do we measure this? So we extract this from these, once we have the period spacing patterns of stars. So once you have the rotation from the slope, you can sort of backtrack or correct for the rotation. And then what you see is the typical spacing is set by this buoyancy travel time, or pi naught, divided by some constant that depends on your spherical degree L. So once you know L as well, you can then extract from these period spacing patterns what pi naught should be. So I've done this modeling using this pi naught combined with the effective temperature and surface gravity of a sample of 37 stars. So what I'm showing you on the plot on the right is the mass and the age that we find using this method. And so we see this sort of mass-age correlation, which is also what we expect from where we expect the stars to pulsate. So that's what I'm showing you on the plot on the left. So you expect only stars to pulsate when they are in this region between the solid lines. So you expect younger, less massive stars to pulsate, and then they stop doing it when they evolve, and for the other ones, it's the other way around. So we kind of recover this correlation using this method. What we cannot really do well is measure the core boundary mixing with this method, but what we can do is measure the core mass quite well. So I'm showing you on the plot on the left is the predicted core mass from hydrodynamical simulations as a function of mass. And so what they find there is that there's quite a good agreement between the predicted core masses from these type of simulations compared to what we've measured for this sample of stars. All right, so now we're gonna move on from using the buoyancy travel time to using the individual mode periods of the G modes, and in addition use the luminosity that we get from the ESA Gaia mission. So we asked whether we can see any correlations between the mass, the age, the rotation, and the core boundary mixing in these stars. So the setup is we use the stellar evolution code MESA. It's a 1D, so that means your star is the same in all radial directions. So we give it a mass, age, 2 parameters for the composition, 2 parameters for the mixing, and then this way we compute a MESA model. And this we couple to the pulsation code Gyre, where we also give it the rotation frequency, and then Gyre gives us the predicted pulsation periods for a given value of L, M, and N. So we compute a grid of models. So here I'm showing you just for different masses, for different mixing, for different ages. And then what we try to do is do this sort of grid search and then select our model that best matches the observations. But yeah, so in practice, it's not really 3D, but more like 6 or 7D. So you have this problem where you have a quite high dimensionality, which means you need a lot of models and a lot of CPU time. So what I try to investigate is whether we could use a neural network as an interpolator for this. So what it means is you compute a relatively coarse grid of stellar models and then use the neural network to train on these models as sort of interpolated, so it can interpolate between these different models. But so first, what is a neural network exactly? So a neural network is based on neurons that are mathematically equivalent to the ones in your brain. So I'm showing you here a very simple example of a neuron with 2 input channels. And so all a neuron does is it takes the weighted sum of both these input channels and then evaluates it in what we call an activation function. So this gives you tells you whether the neuron is triggered or not, so to say. So if you give it an example, so for example, 0, 0 equals 0, 1, 0 equals 0, 0, 1 equals 1, and then ask the neuron to predict what 1, 1 should be. So in this case, it should be equal to 1 because it's the value of the X2 input channel. So what it means is the neuron tries to optimize these weights so that it can predict the output. So what it does in this case, it just gives a large weight to W2 and not so much to W1. But of course, we want to do much more complicated things than that. So what we do is couple these neurons into different layers to form a neural network. So I'm trying to train a neural network for computing pulsation periods and photospheric observables, or C3PO for short. And So I give C3PO a mass, an age, a metallicity, a value for the core boundary mixing, a value for the envelope mixing, a rotation rate, and then it predicts for me the mode periods for different radial orders for L and M equal to 1, as this is the most commonly observed mode geometry in these kinds of stars, as well as the luminosity of the star, the effective temperature, and the surface gravity. So in this way, we find that when we use the individual mode periods instead of the buoyancy travel time for a lot of stars, the mass and age determinations improves quite well. And so what we now can do much better is also measure the value of this core boundary mixing parameter, or this FOV parameter, which gives you the width of this mixing region just outside of the convective core. So my stars are the colored symbols in this plot. So I'm showing it here, the measured FOV parameter that we find as a function of the mass of the star. So in other studies, for example, studies of eclipsing binary systems, they find that this FOV parameter should increase with the mass of the star. But for us, it's not very clear whether this is also the case for these single stars. But of course, we probe quite a narrow mass region as well. But in addition, we also find that for some stars, we need much higher values than what is, for example, found in the study by Claret and Torres, so the plot on the left. So now coming back to the plot that I showed in the very beginning. So here is showing you the rotation frequency, and now instead of the surface gravity, we can measure the actual age of the star. So when we do this, we still observe quite some scatter in the rotation rate as a function of the age. So it's quite, the initial rotation rate is quite significant. What we find as well is that in general, the evolution seems to be quite consistent with the star rotating or evolving as a solid body. All right, so now we're going to move on to the next question, which is microscopic mixing relevant in slowly rotating G-mode pulsators? So here I'm focusing specifically on slowly rotating stars. So we don't have any other type of rotational mixing, for example, that washes out these effects. So yeah, here we try to improve the physics of our current models. So what is microscopic mixing or microscopic diffusion? So I'm using this as a term for 4 different processes. So the first one is gravitational settling. So that means if, for example, you have a glass of water and you put some sand in it, you stir it, and then you leave it, you'll see that the sand starts to sink to the bottom. And similar in stars, everything heavier than hydrogen will start to sink to the center of gravity. We have thermal diffusion, so diffusion between regions that have different temperatures. We have concentration diffusion. So again, if you have a glass of water and you put a drop of ink in it and then you leave it, it starts to diffuse out. And then lastly, we have radiative levitation. So you have photons that come from the core and they transfer momentum onto your atoms, and this sort of levitates them upwards. And so if you have a more massive element, you have more absorption lines to do this with, so then the process is much more efficient. So in contrary to the microscopic mixing, for microscopic mixing, we know this is happening in stars, and we know from first principles how this efficiency should be. But the reason it's not very, or not often used in stellar models is because of the large CPU times that you need to do these sorts of computations. So I studied 2 different slowly rotating G-mode pulsators. So here's one example. So the observed mode periods are the gray lines, and are observed the uncertainty as well. So they're quite small. So we have different mode geometry, so different M values for this star observed. So we do first the exercise where we find the best model where we don't take microscopic diffusion into account. So these are these triangles, and I'm showing the corresponding mass and age of the best model that we find this way. And then we repeat this exercise by now using models where we include microscopic diffusion or microscopic mixing. So for this star, we find that we don't find a better match. So that could maybe mean that there is still some other form of mixing going on in the star now or in the past, or there's still something wrong with our physics. But in any case, the difference in the mass and the age that we find for this star is quite significant compared to the mass range that these kinds of stars cover. So yes, in this case, the models without microscopic diffusion seem to match better. So repeat this exercise again for another star. So again, the models without microscopic diffusion, showing here, and then again, when we include microscopic diffusion, and in this case, we find that the best model is much better to predict the observed frequencies for this star. And in this case as well, the difference in mass and age is quite significant. Yes, so in this case, contrary to the other star, we find that it actually improves our matching with the observations. So going back to the large sample of stars where we model the individual mode periods, so we also find some dichotomy in the sample in the sense that on one hand, we have stars which have period spacing patterns like this, so very smooth. So the observations are in black, and then the best model from the neural network are in red, and then the ones, so afterwards we sort of as a sanity check, recompute the model again with gyre, which are the blue points. So in such cases, we can match the observed pulsations quite well. And then on the other hand, we have stars that look like this. So they have quite some modulation in their period spacing pattern, for which we find, or our models cannot really reproduce these kinds of wiggles. Or we have to go to very low values of this constant mixing in the envelope to even sort of, get close to the amplitude of these modulations that we see in the period spacing pattern. So this begs the question if we can reproduce the observed chemical gradients with microscopic and rotational mixing. So first, what I've done is try to improve the CPU or the runtime of these models when we include microscopic mixing. So if you have a model with different cells, in each cell you have a hydrogen mass fraction, a helium mass fraction, and a metal mass fraction, X, Y, and Z. And so if you have nuclear fusion going on in some of these cells, it means that the X value decreases while your Y increases, but the relative metal fractions or the abundances of your metals, they stay the same. And so to compute your opacity, they depend on these different fractions of the metals. So if you just have no microscopic diffusion, you can have some pre-computed tables for this and then interpolate it. But now if you have microscopic mixing, this is no longer true. So in each of your cells, you have a different mixture or different fractions of your metals, and so this means you can no longer do this like in a very quick way by interpolating between tables, but you have to do this recomputing it every time. So in the MESA evolution code, what it's currently doing is just very brute force compute this every time for each cell at each time step. So it's quite computationally expensive, and as well for the computation of the radiative levitations, this is also actually dependent on the relative fractions of your metals. So what I try to do here is to make a new method where we allow for some tolerance on the different abundances of the elements, such that we can group cells together, and also save computations that have been done before for the next time step. And so this way we find that the increase, or we get a speed up of about a factor 4, which is quite significant considering that to run a model, it takes about a few hours. And so if you want to compute a large grid of models, this is quite significant. So then moving on to the rotational mixing part. So for this, so when your star starts to rotate, it's no longer spherical, but it becomes a bit flattened, like I'm showing you on this illustration on the right. And so in this case, we can no longer use 1D evolution models. And so here we have to go to 2D models. And I'm using the 2D Esther code. So what Esther does is it computes the rotation profile of a star, as I'm showing you in the plot. So the rotation at each point in the star in a self-consistent way. So I'm using these rotation profiles then to predict what the rotational mixing should be, following a formalism from Jean-Paul Jean developed in the 90s. So you have your rotation profile from Esther, and so I'm looking at how this rotation profile changes as a function of the radius and scale the efficiency of the mixing with this derivative. So if you have some shear between different layers, you have much more efficient mixing. And so it also depends on the Bund-Faser frequency and the thermal diffusivity, K. So that leaves us with one free parameter, eta. So what I'm showing you in the plot here is this mixing efficiency that we find using this sort of formalism with the rotation profiles from Esther. And so this is exactly what we need. So in order to get mode trapping, or to have these dips inside of your period spacing pattern, you need to build up a chemical gradient near the core. So you need a very low mixing efficiency near the core. But if you also have microscopic diffusion, because of the settling of helium, you also wash this out. So further out, you need to have actually a higher value of mixing to sort of impede the settling of helium. So in this way, we find in a quite natural way that we get these sort of profiles where the mixing is quite low near the core, and then further out it's high, or it's also higher than what we find if we just use a constant value for this mixing. So what I'm showing you here is the predicted mode period, so the period spacing patterns using microscopic and rotational mixing combined. So it still depends a bit on the value of this eta parameter, of the free parameter. But for certain range, we find that indeed we then observe these trapped mode periods as a function of the evolution of the star. So, and also, yeah, like I said before, this gives us, or we don't have the need anymore for having such extremely low values of constant the radiative envelope. So another cool thing about this formalism is that we can now measure or predict the evolution of the surface abundances, so the abundances of the elements at the surface. So I'm showing you here some surface abundance ratios for carbon, nitrogen, and oxygen. And as well as the magnesium to iron ratio. So that the magnesium to iron ratio is the ratio that we can typically measure the most accurate in these kinds of stars. But unfortunately, our models then predict that this value is more or less constant. So there you couldn't really observe this. But so if we look at the CNO elements, so I'm showing you here the evolution as a function of age for different masses and for different metallicities. And so if we see from these typical uncertainties that we can achieve for these B-type stars or the F-type stars, so the stars that I've been studying, that in principle we should be able to use the surface abundances now as an additional constraint to probe the efficiency of mixing inside stars. So next time you look up at the sky on a warm, clear summer night, I hope you remember that now we have two methods for estimating the stellar mass, the H proxy and the core mass of intermediate mass pulsators. We do not observe any clear correlation with the core boundary mixing efficiency and the mass of the star. We need low mixing coefficients when we assume that this mixing is constant throughout the envelope. And we can now determine the age of a star using the modeling of the individual G-mode periods. Microscopic diffusion is relative in slowly rotating G-mode pulsators, but it does not always explain the observations better. And lastly, that microscopic diffusion combined with rotational mixing is a very promising mixing description for the mixing that's going on inside of intermediate mass stars. Thank you.
Thank you very much for your presentation. First of all, let me introduce the members of the examination committee. I will start with those who are not present here in the room today. First of all, Andrea Miglio from the University of Bologna, Italy, apologizes that he could not attend the presentation today. However, he did send me his contribution, which I will read shortly after those introductions. Then we also welcome today Aaron Dodder from Dartmouth College, New Hampshire in the USA. Hi, Aaron. Then we also have Michel Rietor from Université Paul Sabatier III, Toulouse, France. We then move to those in attendance today here in the room, all from KU Leuven, starting with Tom van Dorselare, who's from the Center for Mathematical Plasma Astrophysics in the Department of Mathematics and Statistics. Then we have Dominique Baumann from the Institute of Astronomy, Department of Physics and Astrophysics, and Astronomy, like that. Then we have the two promoters, Connie Arts, also from the Institute of Astronomy, and then Timothy van Reet, also from the Institute of Astronomy. Finally, I am chairing this committee. I am Thomas Kokolius, also from the Department of Physics and Astronomy from the Institute for Nuclear and Radiation Physics. Moving on now to the discussion with the candidates. I will start by reading the words from Andrea. So Joey, first of all, apologies for not being able to attend your public defense. It was a great pleasure to be involved in the evaluation of your thesis. Your work represents a true step forward in the interpretation of the pulsation spectra of rather complicated objects, laying the foundations for a methodology that will hopefully be applied to larger sample of stars, providing even stronger constraints on the inner workings of intermediate mass stars. While conveying his congratulations to you, but also to the supervisors for this excellent thesis, he still had one more question that he wanted you to address in this forum. The detailed modeling procedure presented in your thesis is applicable to Kepler quality data, for example, with 4 years continuous monitoring. Can you elaborate on the inference on the structure of gamma Doradus stars, which will be possible with the shorter data sets from the TESS and Plateau missions?
Yes, of course, yeah. Oh, excuse me. So the Kepler mission, of course, we have 4 years of uninterrupted data, but for the TESS mission, this is much shorter. So what TESS has done is sort of do a more general scan of the sky, where at best you have a light curve that is about 1 year long. So I still have to really look into detail about the quality of the period spacing patterns that my colleagues can extract with this data. But what I've seen so far is that for 1 year light curve, the quality is not too good to do this forward modeling with. And so for Plato, I'm not sure if they now have the porting strategy fixed, but I think it's they want to do 2 times 2 years. So in that case, I'm a bit more optimistic about what we can do, but it's gonna depend quite strongly on the rotation rate of the star as well. But yeah, I'm afraid the quality that we have from Kepler is not going to be precedented for quite a long time.
Good. Thank you for this very clear answer to his questions. We will then move on to questions from the jury connected online, starting with Aaron.
Hello, Joey. Thank you very much for that presentation. I have actually a sociological question for you, not a science question.
Sounds interesting.
Okay. I would like for you to please describe your experience using open source software to complete your PhD. And in doing so, please list one strength and one weakness of open source software in scientific computing. Thank you.
So the stellar evolution code Mesa that I've used is an open source as well as Jar. I think the core of science is not always to have the right results, but at least to have reproducible results. And so in that sense, I think having the benefit of an open source code is very crucial to doing science as we do. Also because it's open source, such as Mesa, it's supported by quite a large community, and so this also gives you the ability of learning from different communities. So some improvements that have been made for a specific type of star could also be interesting for other groups, for example. For the disadvantages, you still need to have quite some control over the versions of the code itself. So if there's a lot of groups that just take their own version and then start to develop it, and then everyone starts to have their own version at some point, that would be quite a disadvantage. But in general, I am pro open source.
Okay, thank you. Is that all? Do you have another question, Aaron?
No, that's all.
Thank you. Then moving on to Michel.
Hello, Joy, and my congratulations on your work again, and the very nice presentation that you gave. I have just one question, which is still puzzling me, is about these two stars, which show, especially the one where you have better results without microscopic diffusion. And so it's really strange in the sense that you improve the physics and you get worse results. My question is, could that be that the initial conditions on for instance, the chemical profile is not the good one that you started with? I suppose that you are using a homogeneous star as the initial conditions, but or maybe you have other explanation. What would be your idea to sort of solve this problem, this conundrum?
So as I said, these are slowly rotating stars, but that of course doesn't mean they always were slowly rotating stars. So it could be that I think this one was also quite evolved. So it could be that during the first part, there's still some mixing that was dominant or kind of counteracts these effects of atomic diffusion. So what I've also done for this star is so what we did for the models that I showed in this presentation is fix the initial metallicity to the metallicity that we derive from spectroscopy. But so it could also be, of course, that the metallicity that we see now at the surface is not actually the bulk metallicity of the star. So I've also tried to test with models where you start with a solar metallicity to see if that gives a better match. And it does give actually a bit better match than the one where we fix it at the spectroscopic value. So indeed, it could be caused by an error in the assumption of the initial abundances of the star. But what I would like to do for this star is to remodel it now as well with the description of the rotational mixing and see if we can sort of calibrate this free parameter eta as well there to see if we then get actually a much better match compared to the more simple models without microscopic diffusion.
Okay, thank you, Joy, and congratulations again for all this work. Very nice work.
Thank you very much also for your questions and the answers so far. So we will now switch to the questions from the jury members in this audience. Yeah. I will invite you to simply come to ask them here from the mic.
Hello, Joey.
Hi.
Yes, I get some questions, as I usually do, for the final defense to entertain the audience as well. So we discussed previously about the neural network, as you introduced in your presentation as well. And we always discussed about it in a sense that I thought it was constructed in an opposite way. You start from the stellar input parameters and you get the periods out. But whereas normally you would start from the observations and then start get the input parameters of the star. But then you could, this is a discussion we had earlier, so we don't need to take it again. But earlier, so you could also ask the question, can we start from the, not from the frequencies, but can you start from the light curves? That you showed this very nice light curve from Kepler, which spanned several years. Can you feed this into a neural network code and then get the output, completely eliminating the necessity of human intervention?
But so what you would like to do is go from a light curve to extracting the mass H mixing efficiency of a star.
Right. Yes.
Okay, yeah, that's interesting. But so one thing I am not sure about. So yeah, well, we then first, so we now use the MESA models, of course, to train the neural network. So then we still need to develop something that we can go from a MESA model to a light curve. And in addition, so we do quite a lot of cleaning in the light curve as well to correct for instrumental effects and things like that. So you would also, in addition, need to make the neural network quite robust against frequencies that are not pulsation frequencies. So I am very skeptic about doing it in such a way, to be honest.
Yeah, so you really think that the human intervention is still necessary at this stage?
Yeah. Or maybe we can clean the light curves at least to...
Yeah, this is a step you could isolate.
That would solve that problem, but like I said, you still need to then convert the masses H's to a light curve. And another thing, actually, so we don't really know which how I did it now is compute the pulsations in a non-adiabatic way. So that means we don't have no predictive power of which radial orders are excited in these kinds of stars. So to do that as well, I guess, you need to go to some adiabatic formalism where you can then make accurate predictions about which frequencies are indeed excited in these kinds of stars.
So I have a feeling from your answer that neural networks are great, as you showed in your thesis, but in the end, human will always be necessary. And in what sense then can neural networks help to learn about physical effects and physical understanding? Because in a sense, it's a dumb gate system, right? And there are many gates, and you train them with many.
So more in general, so what one of my colleagues is also working on is using neural networks to classify stars. And so if you do it, so you have supervised learning where you define these classes before. But if you do it in an unsupervised way, so you let the neural network decide how it wants to group things. And in that way, you can also discover new physics. So then it might actually come up with a class that has not been known before, for example.
Right.
But for my stars specifically, I'm not sure, to be honest.
Yeah. Okay, let's go to another topic, which you also discussed in your presentation. You showed that together with the astroseismic data, you have also the spectroscopic data on C, N, and O, and that these also give an estimate for the age as coming out from your models. And so I was going to ask, is that not making your work obsolete in the sense that it's better to use a spectroscopic data because that's only requiring one measurement and you get the age immediately?
Well, I wouldn't say that you can really derive the ages from just spectroscopy because you have still quite some degeneracy in the efficiency of the mixing and the mass of the stars. So you still need to have, so I would do it the other way around. So you have a mass and an age of the star, and then you can get more constraints on the mixing efficiency from using the spectroscopy. But just, yeah, having one measurement of these CNO ratios and then get the age, that's probably, yeah, not a good idea because you have such degeneracies in
yes,
in all of your parameters.
In your graphs, you show these typical error bars on the measurements of the abundances. So would it help if you take, instead of one spectroscopic measurement, maybe 10 spectroscopic measurements to reduce the error bars?
Yeah, sure. Yeah, so the error bars that I showed here are from sample where you have quite a mixed bag of signal to noise ratios as well. So they're vary to 150-ish, I think. But yeah, so if we can do a much or do a follow-up where you have multiple spectra and you can combine them to push down or push up the signal to noise to about like 200. So it depends a bit on the rotation rate of the star as well. But yeah, in principle, we should be able to achieve much better constraints on the observational surface abundances indeed. So this is still something I would like to do to get more accurate surface abundances for the sample of stars and then use it as a constraint to see the efficiency of the internal mixing.
Mm-hmm. Thank you. And then the final topic I'd like to discuss is this visibility of the modes, which you discussed in the very last section, if you want to follow in the copy, section 6.4. And this is something we discussed in the first defense as well, which you also adapted the description in the text. And so what I was wondering when reading this part of the text, you look forward, as also in the previous questions, what other data is coming and what will be better than Kepler. And as you said, there's very bleak times. There's no better data coming. But when I was a master student doing my master thesis with Connie, the way to identify stellar pulsators was not with photometry, it was rather with spectroscopy. Mm-hmm. So can you comment a bit on that?
And so in what sense do you mean?
How can we go beyond the current data to future instrumentation using previously established technology like spectrometers, but perhaps going to space? How could you observe a mode there? What more information does it contain than just photometry? How could you exploit that?
So indeed, so as you said, from measuring the variability in the spectral lines, you can also identify modes. I don't have a very good answer on top of my head, I think, for how we can use that for the stars that we study.
Mm-hmm. Well, I was thinking about G modes. They're mostly horizontal motions, so they induce a large Doppler variation, Doppler shift variations, and line profile variations. So then, in principle, that could be very useful for the mode identification, I think, and also for astroseismology, carrying it further using models that you developed, for instance.
Okay, but the mode identification for the gamma dors is in principle not so much a problem, so we can do it based on just measuring the pi naught over the L times L plus 1. So in that case, I don't know if it would give such a benefit to move to spectral variation for these kinds of stars.
Okay, so I guess from your answer, you didn't apply for the ESA call for M-sized class missions to put a spectrometer in space to observe some gamma dor stars for a couple of years?
No, I didn't actually.
You didn't do that. Okay, those are all my questions.
Okay, thank you.
Hi, Jerry. First, a great pleasure and a privilege to read your thesis. It was truly remarkable, fantastic results. And I would like to be the first to say that I think you have a very bright future, whatever you choose to end up doing. And I look forward to following that. Questions. So number one, because there's more than one. So you showed a HR diagram and you showed the parameter space that the Gamma Dorada stars that you've looked at exist in. And the expansion in the sample size has been immense, I would say, in the last few years with papers by Gang Lee, for example. Mm-hmm. I want to turn our attention to the stars in that location that don't pulsate. Do you have a reason why there may be a bias in different parameter regimes where stars should pulsate and don't in the Gamma Dorada instability strip, or in those stars that do pulsate and shouldn't?
Yeah, okay, that's a good question. So one thing I can, of course, blame is the observational constraints. So in general, so for example, the ones in Gang Lee's sample, they are just the effective temperatures are from Kepler itself, so they're not super accurate. But more physical reason could, for example, be that we now don't take this atomic diffusion into account. So for the more massive stars, we also see, for example, that you need to increase the opacity in your iron convection zone to drive these pulsations. So if we might use models with atomic diffusion or microscopic diffusion, you see that you get accumulation of heavy elements around this location, and this in a natural way increases your opacity as well. So this could maybe also be part of how we can explain why some Gamma Dorada stars pulsate while they shouldn't.
So based on your answer to a previous question of TESS being potentially bleak, I was curious if because these stars tend to be a lot brighter, and so the follow-up
in the TESS.
Yes. Yeah. So the follow-up with spectroscopy tends to be a higher payoff.
Yeah.
So perhaps you want to revise your answer just a little bit to say that maybe the trade-off. What's your feeling for the trade-off between having much brighter stars with less photometric data? Do you think they will balance themselves out, or do you want to stand by your statement that TESS is no good for Gamma Dor stars?
Well, I'm not saying like it's not good at all, but for the 1 year light curves, the quality of the period spacing patterns is probably going to be much less. And but the advantage of TESS is at least that it also observes stars in different metallicity regimes. So it is in fact interesting, but I have to look much more into detail about what we can actually do with the 1 year light curves, but it's going to be much less than the 4 years though.
My suspicion is the trade-off from having brighter stars will shrink your spectroscopic error bars sufficiently that maybe it compensates for some of your stars. So that would be an interesting first thing to check, I think.
Yeah.
Second question. I was very surprised that Tom didn't ask this, so I'm going to take the opportunity to ask the magnetic question. So your stars have convective cores. Do we expect magnetic fields to exist there? And if so, can you elaborate on how that impacts your results, if at all?
Yes, so we do expect indeed magnetic fields to exist there. So they're caused by dynamo. So for the Gamma Dorada stars, so measuring this sort of B field that you expect from the differential rotation, if I'm correct, it's estimated it's about like 3 megagauss-ish in the core at best. So the ones that there's, I think, 4 Gamma Dorada or intermediate mass stars that have a surface magnetic field about 1 Gauss, so very, very low. It might affect indeed your G mode. So in other studies by my colleagues as well, that you see that you have this magnetic shift, and this causes these very jagged pulsation or period spacing patterns indeed. It would be interesting indeed to see how we can, because we've never really looked for those type of period spacing patterns in the data so far. So in retrospect, it will be interesting to see if we can also see these signatures of magnetism in there.
So if I was to hire you to look for magnetic fields in your stars, would be that the method that you'd go about doing it, or are there other ways to at least infer the magnetic field strength based on the work that you've already done?
Yeah, so also another way, maybe you're alluding to that, is that, the work by Danielle Leercanet. So what you then there see, what you can do is see which modes are excited, and this also gives you an upper limit, if I'm correct, on the magnetic field strength. But so yeah, that has been done for a more massive star, so I'm not sure if the Daedalus code that they use for it is also applicable for these lower mass range, but that would indeed also be a way to go.
We've had to hold Daniel back from emailing you until today, so maybe we'll get some emails in the near future. Last question, which I think you've already alluded to in your answer, but maybe just to clarify a bit. So there is a problem in Gamma Dor stars, is that far too many modes seem to be excited compared to the predictions from models, this non-adiabatic prediction of which modes should be excited. So do you have any thoughts about how to go about maybe addressing that? Which physics is missing from your work? Or
improving the prediction of the excitations of the modes.
To try and explain the large range of radial orders that we see for your stars. Where would you put your effort?
Mm-hmm. Yeah, I think I would also see indeed if we can change the opacity profile with models with atomic diffusion. So I'm not sure how exactly the opacity is going to change the radial orders that are excited. I think that's the only way I can come up right now to do.
Mm-hmm. Do you see any correlation between the rotation of the star and the number of radial orders? I probably should have asked this in the internal because I never actually looked this up myself, but is there any correlation between the rotation and the number of radial orders that you see in your stars, or is it a bit smeared?
That's a good question. I tend to say indeed that the ones that we have quite a large range of radial orders are the ones that are most rapidly rotating. Mm-hmm. But yeah, I'm not sure if it's one-to-one correlation in the whole sample.
Sure. Okay, thank you, and congratulations again.
Thank you.
Joey, congratulations on very nice work for the last 4 years and on a very nice presentation. As a supervisor, I mean, we've had a lot of discussions over the last 4 years. We've already asked each other quite a lot of questions, so I will take this opportunity to, for once, not ask you a question. Right. Thank you.
Well, I cannot copy that. That's too boring. So, Joey, I will say a few more words later on, but still I have one question.
All right.
There was no time because the other jury members were so intense in their questioning in the internal exam. I couldn't discuss with you on this eta parameter. Mm-hmm. I'm intrigued by this eta parameter. So let's say you have 6 more months, right? Mm-hmm. And you can do a new exercise of modeling, which you already alluded to in the answer to Michelle's question. Would you then upgrade your dimensionality on eta, or would you put in let's say an observed rotation profile from an inversion that some of the people in the audience are delivering to you, or a magnetic field profile? What would you do, or all that together? Can your neurons deal with that?
Yes. So one thing I would like to do is couple really in real time the STR code with MESA. So right now I'm getting the rotation profile, so it's context for the audience as well, to as an interpolation for different masses. So I compute it for a few masses and then do the interpolation, and also in the H. So if we can really real time couple STR to MESA, so that STR gives MESA the rotation profile, and MESA gives STR the core mass as a function of time. So as there are static models, I forgot to say that actually. Yeah, so that would be something I'm very passionate about to do this. Yeah. So what was your question for the calibration of
The eta?
Yeah.
Is that included in what you just said or not really?
So I think for that, yeah, we really need quite accurate spectroscopic measurements to put constraints on this eta parameter. So one thing, yes, I've not mentioned, but it's actually sort of a physical origin. So if you look at the formulism from Jean-Paul Jean or from Stéphane Matisse, for example, so it actually sets the ratio of the thermal diffusivity to the horizontal diffusion, the horizontal diffusion, or the other way around. I don't remember. So yeah, I'm not too deep in the theory there, so I'm not sure if that value would be the same for all stars. But yeah, if we can actually observe or calibrate this observationally, that would also give some more insight on the physics there.
Okay, that seems like an excellent thing to do with one of your jury members. Thank you.
Thank you to all the members of the jury. Although it is not standard, I will allow myself a question as well. Maybe not of the same caliber of level as some of the others, but nonetheless, something that intrigues me. Imagine you are standing on a planet orbiting one of the pulsating gamma Doradus stars you've described to us today. Would a person there observe this pulsation, and if so, in what form?
You just mean by the naked eye, or
by the naked eye? What would be your perception of those if you were, or to return it, if our sun was one of those gamma Doradus pulsators? How would we observe that in our simple way?
Yeah, that's a good question. So the amplitudes that we measure for these kinds of modes are millimagnitudes. So I've sort of tried to do this back of the hand calculation, and so the actual physical change in the radius of the star is 1,000th of a percent. So I don't think you will actually be able to see this with the naked eye.
Okay.
But yeah, I'm not sure how it scales with the sun. So our sun has these pressure modes as well, for example. Yeah, we don't see them with the naked eye as well, of course. But yeah, I'm not sure how the amplitudes relate to the ones in the sun.
Okay.
It's sort of same caliber. Yeah.
Good. Seems reasonable indeed. Very good. I am now turning to the audience to see if there are any questions. Now is your time. And do we have a monitor for the online participants? And are there any questions? I don't see any coming up. One time, 2 times, 3 times. Thank you very much. The jury will now retire. Ladies and gentlemen, dear colleagues, I will now proclaim the results of the deliberation by the examination committee appointed for the doctoral degree in science, astronomy and astrophysics. Mr. Joey Stephanus Gradus Mombarg has presented to the faculty his PhD thesis on the topic Asteroseismic Modeling of Intermediate Mass Stars, in partial fulfillment of the requirements for the PhD in science, astronomy and astrophysics, and he has defended his thesis in a public session before the examination committee. The examination committee has determined that all requirements concerning the granting of the doctoral degree that are prescribed by the law and by the university regulations have been met. Therefore, on behalf of the rector of KU Leuven, I confer upon Mr. Joey Stephanus Gradus Mombarg the degree of Doctor in Science, Astronomy and Astrophysics, and I hereby close the session. So I believe now that the promoters have a few words.
Beste Joey, beste dokter Joey, eerst en vooral heel erg gefeliciteerd, van harte proficiat. Na 4 jaar heel hard werken heb je dubbel en dik verdiend jouw doctoraat gehaald. Het zijn 4 heel interessante jaren geweest. Hopelijk evenveel voor jou als voor ons. En dat was zeker voor mij het geval, want jij was de eerste doctoraatstudent die ik ooit mee zelf heb begeleid. Een kleine 5 jaar geleden kreeg ik een bericht van Connie. Er was een nogal stille, maar slimme student die haar vak astroseismology volgde aan de Universiteit van Nijmegen. En die wou bij ons een zomerstage komen doen. En waren er nu geen interessante sterren in dat sample van Gamma Doradus-sterren die dringend gemodelleerd moesten worden? We hebben er dan eentje voor jou uitgekozen. En je hebt er dan in augustus 2017 heel hard aan gewerkt. Maar aan het einde van dat zomerproject was eigenlijk vooral duidelijk geworden dat er nog veel meer werk aan gedaan moest worden dan wat je in die ene maand kon doen. Je hebt het daar dan niet bij gelaten. We hadden dringend een gemotiveerde doctoraatstudent nodig. En ja, zo ben je na het afstuderen in Nederland ben je dan 4 jaar geleden hier in Leuven aan je doctoraat begonnen. Het doorzettingsvermogen dat je hebt laten zien tijdens dat zomerproject, dat is een rode draad gebleven tijdens die 4 jaar. En met als resultaat een heel mooie thesis met een heel brede impact. Het is duidelijk gebleken, je bent niet alleen een heel goede onderzoeker, maar zoals we ook daarnet al hebben gezegd, je bent ook iemand op wie je kan rekenen en vooral voor wie waar het heel tof is om mee samen te werken. Dus Joey, bedankt voor deze 4 leuke en heel interessante jaren. Dank je wel.
Van harte gefeliciteerd, Dr. Joey. En wat fijn, heel fijn om in Leuven ook nog eens een laudatio in het Nederlands te kunnen doen voor de familie. Dat is geleden van toen jouw co-promotor afstudeerde. How time flies. Hè? Ja, toen jij hier aan jouw doctoraat begon, Joey, toen introduceerde je jezelf aan ons team als Timothy 2.0. Nog altijd ben ik in de war en daar straks heb ik zelfs nog de fout gemaakt door Timothy aan te spreken met Joey en jou aan te spreken met Timothy. Nee, jij bent niet. You are not Timothy 2.0. You are Joey 1.0. What an embarrassment I always have to face. It's even changed now today. It's Dr. Joey 1.0. Huh? And that's a great feeling I think you have right now. It's true, on the other hand, that you share some characteristics with Timothy. You are both rather shy. You use few words, unlike me. And you are both in love with Gamma Doradus stars. But you are also very different in some aspects, if I may say so. Although the three of us, we do share the same, well, one same passion. Huh? We care a lot for very high quality coffee products. And we shall keep on adhering to that quality. You and I also share some common interests that are perhaps not so much associated with Timothy. The one on top, I would say, composing fabulous acronyms. We are the champion of that. Also doing science outreach, I think belongs in that category. Also undertaking international travel and residing abroad. We love that. And along with it, we proactively tend to search for international collaborators that are a good match with us. So in this regard, and we still see him on the screen, I'd like to thank sincerely Aaron Dotter, because he hosted you in Harvard back in 2019. According to Aaron, that was 5 or 6 years ago, but that's not true. So it seems like ages. And that's because, well, it led to some very interesting collaborations. So Aaron, thank you for having hosted Joey. It was only 3 days he was with you at the CFA, but this interaction meant so much for him that this became the seed of an excellent collaboration from which you, Joey, really benefited a lot, and it cranked up your self-confidence in coding Fortran in Mesa. How nice. Yeah. Similarly, Michelle, I'd also like to thank you a lot, another key collaborator who hosted you in Toulouse for about 7 months, despite COVID challenges, I should say. And I know that Michelle has spent quite some time in upgrading your knowledge on hydrodynamics and the theory of transport processes in stars, following the French school in that topic. And he even managed to make you pronounce Esther, yes, rather than Esther. So keep going, Michelle. French accents are improving. So thank you both, Aaron and Michelle, for having been part of Joey's supervision. We were actually a quartet together with Timothy and me, and I think the four of us sort of managed well, if I may say so, in arming Joey with a very broad set of skills that will come in handy for the continuation of your academic career. And so I will be very glad to send off Joey to Toulouse, but only after keeping him here for a while, because there are a few more months that he can fill some projects where I am convinced that he is the best one in the world to treat them. So I'm kind of triggering that, and you have to prove me right on that one. All right. Also because it will allow you to transfer some wisdom to some of the team members in the audience. So this actually brings me to my PhD students in the audience. Here's a challenge. It becomes ever more difficult in my case to be my first PhD student in something, right? And so Joey managed quite well. You might not realize it, but you did splendidly, because you're the first PhD student of mine to have handed in your thesis 1 week before the deadline for my review. Please take note, 1 full week before the deadline. It was in my office. All right. This is something that perhaps if I were to be allowed to point out one quality of Dr. Joey 1.0 to colleagues or committees worldwide. It's actually your result-oriented approach. No nonsense Dutch route to reality. I really like that. And your thesis has 4 first author papers and 7 more additional ones with well-deserved co-authorships. I think that's excellent and carefully timed output, Joey, which really deserves a congratulation. Huh? It's going to be also a big asset for your academic career that you are pursuing right now and will pursue in the near future. Right. There's another thing I haven't finished with messages to my PhD students in the audience. Joey also has already a list of scientific prizes and awards, even before your PhD defense. 2 international best poster prizes and a very prestigious award from the Koninklijke Hollandse Maatschappij der Wetenschappen. You remember how we enjoyed that, right? Beste masterthesis in de sterrenkunde in Nederland. Best masterthesis in astronomy in the Netherlands, which is quite impressive. Huh? A thesis where you showed your love and developed it for neural networks. Wat ben ik blij voor jou dat wij hier vandaag samen zijn om deze successen te vieren, Joey, samen met de familie. Vrienden uit Nederland en ook collega's die speciaal vandaag teruggekomen zijn uit het buitenland naar Leuven. En anderen die online meevolgen. Je was daar erg nerveus over. Ja? Zoals je nogal nerveus durft zijn over sommige dingen. Maar de gedachte om je PhD voor een computerscherm te verdedigen, dat was er geen. Ja. Sommigen hebben dat moeten doen. En het had dan ook zo moeten zijn, maar het is toch leuk dat we hier samen zijn vandaag. Het was nipt wat COVID betreft, maar ook daarin perfecte timing. Perfect timing to achieve that. Dus laat mij daarom snel eindigen, zodat we alle samen kunnen gaan klinken op Joey's succes, maar niet vooraleer toch je familie uit Nederland ook welkom te heten, maar vooral te bedanken voor het uitsturen van hun zoon, broer, vriend naar het zuidelijke Leuven. Wij promotoren, en dan spreek ik toch in naam van Timothy, ik heb bijna fout gedaan, en mijzelf, konden ons geen betere zendeling vanuit Nijmegen inbeelden. Dank jullie wel dat hij hier mocht werken bij ons en nog zal werken, want dat was een gouden geschenk. Dear Dr. Joey, sincere congratulations from your supervisors. We look forward to continue our collaboration. En dat ga je heel goed op je verdere loopbaanpad. Timothy en ik hebben cadeautjes mee, dat gaan we straks doen. Maar ik kan alvast vertellen dat ze zijn om te ontspannen.
Okay.
Congratulations.
Thank you. So I would like to thank everyone as well for being here. It means the world to me that you are here with me today, and for the people online that joined online, of course. So in the Netherlands, if you defend your PhD, you also present 10 propositions that come with it. So these are kind of general lessons learned during your PhD. So in the Dutch spirit of that, here are mine. All right, so there we go. Number 1, the summer project with a strict Flemish professor and her postdoc has been successful. Yes, thank you both so much for all of your guidance throughout the years, and thank you for giving me this opportunity. I'm so grateful for that. Secondly, you cannot take a pot of hair wax with you on an airplane. Thank you, Dominic. So these are actually things that are kind of my cheesy way of thanking people that were there when I learned these valuable life lessons. Everything is spicy in India. Thank you, Sriya. Number 4, if you like your knees, don't take taekwondo lessons with me. Thank you, Mike. For the record, it was not actually my fault. Pizza, Mountain Dew, and frozen pudding are the holy trifecta of the Santa Barbara University canteen. Thank you, Andrew and Robin. Don't say at a poster pitch that you do the same as your colleague, but more difficult. Thank you, Matthias. Never meet your heroes unless it's DJ Marcel. Thank you, Garrett, Callum, JP, and Simon. If you go to Budapest in the summer, just stay at Aquaworld. Thank you, Emily. If you rent a car, make sure you have enough spending limit on your credit card. Thank you, Luke, Stefano, Mom, and Ari. Lastly, doing a PhD during a pandemic is hard, but it's possible when you have friends and family to pick you up once in a while. Thank you, everyone. So I'd like to cut the stream for here. So thanks again, people at home, for joining in. And I hope I can celebrate with you in the not too distant future. Bye-bye.